Hello everybody, this is Professor Lombardo. In today's lecture, we're going to use what we know about probability, specifically the central limit theorem, to build an understanding for our first inferential statistics technique, something called a confidence interval. We'll start by reviewing our central limit theorem, and then we'll start to build that bridge towards understanding what a confidence interval is, what it does, and where some of the formulas come from. As a quick review of the central limit theorem, remember the idea is to view the sample mean that you would get as a researcher by taking a random sample from the population and computing the sample mean. We want to view the sample mean as being a random variable. And it really is random, the value you're going to get, because remember the way that we create our samples is we take a random collection, a random smaller collection from the population. And since our sampling method is random, we could end up with any number of different possible samples, which of course would also lead to different sample means as well. So this value that we're interested in studying, this sample mean, truly can be thought of as a random variable. What the central limit theorem does is it makes predictions as to where those sample means are going to fall based on this underlying random sampling process. So specifically, one way to envision this is to think about generating a whole bunch of different random samples from that population and looking at what their sample means would look like, and then treating this collection of sample means as a data set. And then we can ask sort of unit one type of questions about it. What would its histogram look like? Where would the balance point or the mean for that histogram be, right? What would the mean of these sample means be? How much variation would there be? What's the standard deviation of the sample mean? The central limit theorem gives us predictions or answers to all of those questions. Right? So regardless of what our population distribution looks like, if we assume that we have enough samples, we're collecting at least 30 observations or more, the sampling distribution, right, as a histogram is going to have a nice normal shape. In other words, we can use the normal probability distribution as a model for the sample mean distribution. Moreover, it tells us a little bit something about where that peak's going to be and how much variation to expect. The peak of our sampling distribution for x bar, right, for that sample mean, is going to be exactly at the balance point for our original population. It's going to be at the mean of our original population. The standard deviation, sigma of x bar, gets updated. It starts with the original variation in the upper population and then divides it out by the square root of our sample size. Right? So what the central limit theorem essentially tells us is by looking at sample means, we get a very predictable probability distribution with a predictable center and a predictable variation. And this is very powerful information. So our next step is we're going to try to leverage this into creating what we'll call a confidence interval. So here's the idea behind a confidence interval. Our main goal here is to try to figure out what the population mean is from taking a sample and looking at the sample mean. Now, from the central limit theorem, we can conclude a couple of things. First of all, right, remember the peak of that sampling distribution, the peak of the x bar distribution occurred at mu. And typically what this means is that the sample mean that you're likely to get, right? Remember the peak is where you're most likely to get values. So the sample mean that you're most likely to collect is going to be close to the population mean. Now this is really good news. This means that our sample mean, generally speaking, is going to be pretty close to the value we're trying to figure out. Unfortunately, while it's going to be close, it's not going to equal it in general, right? The sample mean's never going to perfectly hit that population mean. Because again, we're only looking at a piece of that population. We're not looking at the whole thing. We're working with a sample. So the great idea behind a confidence interval is that, well, rather than trying to guess the population mean perfectly, why don't we kind of give a little bit of error, allow for a little bit of up and down? So what we do instead is we consider an interval centered around x bar. Remember, x bar is a really good guess from our first bullet here. X bar is a really good guess for where mu actually falls. But if we consider an interval centered around x bar, we can kind of increase the likelihood of actually capturing that mu, actually capturing that population mean. Right? So I have a really good visualization for this. Okay, on the plot on the left here, what we see is these green dots. This is representing an entire population of different plant heights. And the green line running across the middle here, this is the actual population mean. Now what we're going to do, you can see we now have a plot over here on the right. This is going to keep track of different sample means that we collect by getting a random sample from the population. I'm going to start out with a sample size of 5 here, and I'll show you what happens. If I click the Get One Sample, let's zoom in here again. You can see that there are 5 dots, 1, 2, 3, 4, 5, highlighted in blue. This is the random sample that we've collected from our population. And the sample mean coming from that sample is now plotted across here in a dotted blue line. And that sample mean, you can see, gets transferred over to the right. Now, as I click different samples, you'll see that the dots switch around because I'm sampling randomly from the population. And over on the right, I just get a catalog of all the different sample means that I've collected up until this point. Now notice that the green, which remember is our actual population mean, typically speaking, the sample means that we're collecting are close but not equal to that population mean. So even though we're getting close, we're technically missing that population value. The main idea behind a confidence interval is to just say, well, rather than trying to hit the green line with a dot, try to hit it with an interval. So what we're going to do is for each actual sample mean estimate, rather than just considering that exact value, we're going to widen by some fixed value, right? We're just going to widen by a little length up and down. We'll call this thing a margin of error, which hopefully sounds familiar to you from our middle percents. And the idea is now that the interval itself actually does overlap with that population mean. So the population mean is sort of captured by the confidence interval itself, right? Now, what I'm going to do here is I'm going to start collecting a whole bunch of samples. So we can do this over and over and over and over again. And what we'll see is that in, I think, about 350 different samples, only one of the random samples that I collected led to an interval that didn't actually overlap with the green. It's highlighted in red here. So we can talk about what the success rate for this type of process would be. We'll eventually call this thing a confidence level. But loosely speaking, what it does is it says, of all the different sample means and hence confidence intervals that we could generate, how many of those confidence intervals end up overlapping with the actual population mean? Now, one thing you'll notice is as we increase our sample size, right, as we collect more blue dots from that population, one thing we'll see with our confidence interval formulas is that the length of that margin of error, right, the length of the interval that we end up using to try to capture that population mean is going to get smaller. But what we won't see here is too much of a sacrifice in the success rate. Right? We're still operating at 97% of the confidence interval processes that we've gone through so far actually capture that population mean. So we'll still have a very good confidence level in this process. Just as a recap, x bar is going to be pretty close to mu, but generally speaking, it's going to miss it every time. So rather than just using a single point estimate, right, a single number, our sample mean, to estimate mu, what we're going to do instead is use an interval, because the interval is more likely to have mu inside of it than you are to actually hit the mu with your sample mean. So this leads to a very interesting question. Well, how far should we move away from that best guess, that x bar, our sample mean estimate, to create our confidence interval, right? It's a bit of a Goldilocks situation because on the one hand, you could make your confidence interval so wide that you're just guaranteed to actually capture the population mean. So for example, suppose I wanted to estimate the age of people going back to night school, right? Well, if I used as a margin of error 50 years, regardless of what sample mean I get, 50 years on either end is going to capture that population mean age because it spans 100 years. Then again, if I don't widen enough, I'm not likely to actually capture that sample mean. If I, for example, only use a margin of error of like 1 year, then the sample mean I'm going to collect, let's suppose my sample mean is 42 years of age, right? Then my confidence interval would be between 41 and 43 years. And that seems kind of too slim to actually capture our mu with a high probability. So what we want to do is kind of pick this distance that's just right. We want it to be wide enough so that we're increasing our likelihood of actually finding mu, but not so wide that we're making the interval too big and kind of not really communicating much information.